Hi guys, today I would like to welcome you on my today's report on fluxgate transducers in high voltage application. And today we want to have a look at the detection of small DC currents at large 50 Hz amplitudes. I have performed some measurements with Alexander Lübke from Hubert Göbel, and so it's a teamwork from SENSELEQ and Hubert Göbel. Yeah, as you can see here, we have the grid frequency, which is in Europe 50 Hz, and every equipment is specified for this 50 Hz frequency. And in the last years, we had a look at the harmonics and the supraharmonics because of the nonlinear lots and all the renewables which were integrated into the grid. So today we have a look at the DC component, where we can find DC components and so on. And the big question is, can we measure these small parasitic DC components with our technology? The first source of a small DC component is coming from the GICs, from the geomagnetically induced currents from the sun to the power grid, and around 120 kilometers above us there can be an electric jet of around 1 million amps, and here you can see the dimensions of those electrojets. And of course a flowing current has a magnetic field, and we can find here in the high voltage network a closed loop, because all the star points of the transformers are earthed. So in this closed loop, the magnetic field can induce a small DC component in the network. In addition, a lot of metros or trams have a DC power supply. So here the supply current is a DC current, and it's going back on the railroad track, but this is not perfectly isolated from Earth, so you have stray currents going into buried metal pipes or into the grid. And of course here you can see how it enters an earth star point of a transformer. And so you can have everywhere a DC component where you have earthed networks. Yeah, here in the grid we have a lot of inductive devices like voltage transformers, current transformers, and of course power transformers. And here you can see what happens with those devices if there is a small DC offset. In this picture you can see here the BH curve of the core material, and everything is all right. This is a magnetization current of the transformer. And here on the right side, if there is a DC offset, it's going deeply into saturation, and the magnetization current increases. And of course it depends on the transformer what kind of losses you get from a DC component. But here I've find some sources in the internet where a single phase transformer produced 30% more losses with a load of 1 amp DC in the test. So, and of course if we have saturation effects, a small DC current can lead to an increase in noise. Here in this example, 140 milliamps increase the noise of 17 decibel. Yeah, as we learned, a small DC component has a negative impact on our inductive devices in the grid. And of course, corrosion of metals can be caused by a DC component as well. And so there are a lot of unwanted phenomena due to the DC offset. So in the medium voltage or in the high voltage, we don't have special rules with maximum values for the DC component, but we can find some maximum values in the low voltage standardization. And here I've copied a paragraph out of the TRR low voltage in Germany. TRRs, these are technical rules for the connection and operation of customer installations to the low voltage network. And here we can read, here in English, a converter shall not inject more than 0.5% of its rated current or a maximum of 20 milliamps. The higher value shall be selected as direct current. So there's definitely a maximum value for example, solar converters and so on. Yeah, we have here in Germany a maximum value of 20 milliamps, but here I found an IEEE paper from 2019. They've investigated 3 different types of inverters, and they found a quite high DC offset for 2 of them. 74 milliamps for the type A inverter, type B with 23 milliamps, and only the type C inverter is okay according to the German standard. But there are also other nonlinear loads which can generate a DC component in the low voltage grid. We have here, for example, a bridge rectifier, which is built in computers, for example. And here is the electrical circuit diagram. And what we can see here is that this circuit has 4 different diodes to rectify the AC signal. And every electrical load can be described by a current voltage curve, and this red line is the characterization of a bridge rectifier. And if you have here a little bit of asymmetry, which is caused by small differences in the diodes, you can generate a small DC component because of this asymmetry, as you can see here. Though this is a bigger 50 Hertz half cycle than the positive one. So that means we have here a small DC offset. And on the right side here you can see a table from different computers, and they all have a DC component, and in the average value is 11.3 milliamps. And if you sum up all these milliamps with 10 computers, for example, you can have something around 130 milliamp DC only with a small office. Yeah, for the test setup to detect very small DC components with a big 50 Hertz amplitude, we use a SENSELEQ flux gate currents transducer here in cast resin with around 400 millimeters inner diameter, which is for bushings in switchgears or big power transformers. Yeah, and here we have the electronic module which is necessary to have a correct working transducer. And for this flux gate transducer has a special design which is called balanced core design. And with this balanced core design, we have the most accurate flux gate current transducer design you can get in the world. So here you can see that 2 cores are relevant for the DC component and subharmonics, and this is the AC core, and everything is coming together, and the compensation current is flowing through 3 cores, and so we don't have any high amplitudes of the induction in those cores. So every magnetic fields in the cores are compensated by this secondary current. Yeah, this special current transformer can measure up to 50 kiloamps for 1 second. And we have a rated primary current of 2500 amps. And of course the rated insulation level is only low voltage because we have the insulated bushings, and rated frequency is 50 Hertz. Yeah, and the rated secondary current is 1 amp. And now we have a look at the accuracy, and here we have the amplitude error. Here the green line is very accurate, and here the classes, the IEC classes according to the IEC 61869-2. This is the highest class you can get, 0.1, and this is our flux gate transducer. And here for the phase displacement we have a very high accuracy as well. So everything is okay. We have a very nice sensor for testing. Yeah, here you can see our test setup. We are generating here 800 amps RMS at 50 Hertz. And we have here the DC component. We start with a small DC component, and afterwards we generate a 1 Hertz signal. So we have also a simulation for GIC currents, which have a frequency between DC and 1 Hertz. So we will test both DC and 1 Hertz of the small signal. And as a reference, we have here a high precision shunt in this circuit, and in the measurement device detects our flux gate transducer and the shunt of the small DC circuit. Here you can see what kind of voltage levels we have at the input channels. For the device under test, we have 0.32 volt at 800 amps 50 Hertz, and we have only 0.00004 volt at 0.1 amp DC. So we have very low levels on the input channel of the reference, and of course of the DC component, which is detected by this current sensor. Yeah, we start here with 10 milliamps. You can see here the cursor of the recorder. And here we are at 10 milliamps. We can see the DC component, and we have, of course, some low pass filtering. And yeah, these are the values. And we have the big 800 amp 50 Hertz amplitude RMS value. This is the oscilloscope, unfortunately without a fitting trigger. And here the FFT analysis of the 800 amp amplitude at 50 Hertz, the biggest value, of course. And here we have the flexible FFT analysis, where we can see here the DC component. And yeah, we are now at 50 milliamps, and this is already very accurate in my opinion. And yeah, it looks like that we can measure 50 milliamps very precisely. And now we go to the 100 milliamps, and yeah, I think it's very stable, the signal, and yeah. Now we come to 1 amp. And here we can see the FFT analysis. So as a result, we can say that we can measure very small DC components, even with a very big inner diameter and a big 50 Hertz amplitude. No problem. And now the test measurement for the DC component is ending. Yeah, here we have started now the measurement with a 1 Hertz component, and we are here at 10 milliamps, and we can see here that we have something like an offset of 20 milliamps, and we have here the 50 Hertz amplitude of 800 amps. And yeah, here we have the FFT analysis that we can, here we have 0, here have we 1 Hertz. So we have a big DC offset here in this measurement. Maybe we could get better results if we compensate these DC offset. But okay, now we have to live with it. Okay, we have here the FFT analysis of the 800 amp signal, 50 Hertz, and some harmonics in the frequency range up to 1000 amps. Here is the oscilloscope, and here we are at 10 milliamps, still at 40 milliamps after the sensing part of the flux gate transducer. As you can see here, it's very small, but these are RMS values. And we now switch to 50 milliamps in a few seconds. Here we can see, now have a look at the FFT analysis. There should be now a bigger 1 Hertz component. Yes. It took some time, but we now see the big 1 Hertz component here, and we still have a DC offset in this measurement. So it would be good if you have a power quality analyzer which can compensate the DC offset in those measurements, because then you can be more precise. But I would say we are here in the 50 milliamp range. We are very stable, and it's still a quite good measurement for the big inner diameter of 400 millimeters. So a lot of electromagnetic fields could couple in. So now we reach the 100 milliamp in a few seconds. Yeah, it takes some time to calculate the right RMS value, but here we are, 100 milliamps. So, yeah, still a good measurement with the 1 Hertz component. It is recommended to have a DC compensation tool in your power quality analyzer. So thank you for your attention and see you soon.